Hello everyone. So in the last lecture we have seen an important technique which is called as a soul gel technique, and we have tried to understand what is the meaning of soul, what is gel, how different reactions stages of the soul gel technique has gone through in order to get a gel. And once you get a gel, then you are able to make a very important material from this technique, which is called as an aerogel. Okay, so aerogel is a material um, which can be synthesized by using this soul gel technique. In addition to this aerogel, we have also seen that this gel can be converted into zero gel, and if you grind that zero gel, then what you get, the final product is in the form of powder. Or that zero gel you can also sinter in order to get a dense ceramic. Okay, so these are the ways by which you are able to make a zero gel, powder, or aerosol. Okay, now in this lecture we are trying to focus on the coating techniques by using this soul gel technique. Okay, so when there is a soul is present, so instead of converted into gel, we can also use that soul for different types of coating processes, and with the help of that process we are able to get the material in the form of a thin film. So in this lecture we are trying to focus our attention on soul gel technique for coating of thin films. So basically we are trying to understand this coating process based on three different coating techniques. Okay, one is called as a flow coating process. Okay, second is called as a spin coating, and third one is called as deep coating. So these are the three ways by which we are able to use this soul gel for coating process. So let us try to understand these techniques one by one. So in this slide, what you can see, there is a schematic image where there is a bath tub is present. Okay, the substrate is also present, and what you can see is there is a probe. Okay, there is a conical probe is there, through which you are able to insert the soul, and you can start from one end and you can take it to the other end, and then you can see that the arrows which are indicating are nothing but the coating of this soul on this substrate. So this kind of type of coating is called as a flow coating process. So in the flow coating process, the liquid coating system is poured over the substrate to the coated. So you have a substrate, and you have to pour, you have to um, you have to pour the liquid, okay, in such a way that it will keep flowing on the substrate. So obviously if the liquid is required to flow on the substrate, then what is necessary, the angle of inclination of substrate is necessary. If the substrate is horizontal, then it is not able to flow over the substrate. Okay, so what you have to do is you have to tilt that substrate at a certain angle. So the coating thickness, okay, so the thickness of the coated material is depends on the angle of inclination of substrate. Okay, this is one point. So the coating thickness is depends upon the angle of inclination of substrate, and second point is liquid viscosity. Okay, liquid viscosity. And the third important point is solvent evaporation rate. Okay, now let us try to understand one by one. Okay, so suppose you want a very thick coating. Okay, if you want thick coating, then what should be the angle of inclination of the substrate? It should be low. Okay, so if you keep the angle of inclination is low, then the speed with which this sole is flowing on the substrate is very less. Okay, because the angle is less. Okay, so in that case what happens, you get more and more coating, so that the thickness of the coating is higher. Okay, so if the angle of inclination of the substrate is very high, okay, very high means at the max you can keep 90 degree. Okay, so it should be from you can vary this angle of inclination of the substrate from 10 to 90. Okay, so in that case you will able to get some coating. Okay, so when it is a 90 degree, then the thickness of the coating will be low. Okay, so this is a one point. Second is, suppose the angle of inclination of substrate is constant. Okay, and you are varying the viscosity of the liquid. Okay, so you are aware that if the viscosity is very high, okay, then the thickness of the coating will be more. Okay, it will be thick coating. If the viscosity of the liquid is low, then what happens, you get a thin coating. So accordingly you are able to control the thickness of these coatings. And the last point is the solvent evaporation rate. Now which type of solvent you are using? Okay, if it's a evaporation rate is very low, okay, it is not evaporating immediately, then what happens, the coating thickness is very high. Okay, if the solvent evaporation rate is very fast, okay, then the coating thickness will be low. So accordingly you have to choose this parameter in order to control the thickness of the coating. The advantage of the flow coating process is that non-planar large substrates can be coated rather easily. Okay, so what is the importance of this substrate? Suppose what is the importance of this coating process? Suppose uh, your substrates are large enough and they are not planar. Okay, they are with a different shape and size. Then what you can do is you can use this flow coating process in order to coat these materials. The second important technique which most of you will be able to use it in our day-to-day laboratories, okay, is a a spin coating process. The sol gel based spin coating process. So the spin coating is used for making a thin coating on relatively flat substrates. Now here you have to keep in mind that for spin coating the substrate, okay, the substrate should be exactly horizontal, it should be exactly flat, it should not be inclined with any angle. Okay, so you need as flat as, okay, as flat as the substrate. The material to be made into coating is dissolved or dispersed into a solvent and then deposited into the surface and spun off to leave a uniform layer for subsequent processing stages. So what you can do is, suppose you want to make a zinc oxide thin film, then what you can do is you can make a sole of zinc oxide nanoparticles, okay, and they are suspended in the solution, colloidal particles of zinc oxide, they are suspended in the solution, and then that you can use it for the deposition of zinc oxide thin film. So you can use this spin coating technique in that case where your nanoparticles will get deposited uniformly on the surface of the substrate. So spin coating is one of the most common technique for applying thin films to substrate. It is most common because it is low cost, it is easily available. Okay, you don't need very high sophisticated techniques, so you can easily use it in your laboratory purpose. The advantage of spin coating is its ability to quickly and easily produce very uniform films ranging from few nanometers to few microns in thickness. Okay, so this is very important, that a simple technique, you can use it for deposition of thin films, and you are able to control the thickness from nanometer to micrometer scale. So you can see the schematic image of this spin coater technique. I have taken this image from the website of Oscilla. Oscilla is one of the international company who is basically producing a very high quality spin coater machine. Okay, so you can see they have very well equipped in a very short size. Okay, in a very small size, they have prepared this type of a technique. So here what you can see is there are different types of this system. Okay, for example, you can see there is a screen is there. Okay, so that is a display, and yet it is used to set the parameters of spin coating. Okay, second one you can see is a commercial chunk, sorry, is a customized chunk. So you can use it as a chunk where you can insert your substrate, and they have made a groove inside a Teflon liner, a Teflon slab, where with that size you are able to insert the substrate. In some other cases, what they can do is they can give you a small liner where you can keep your substrate and you can insert a vacuum, so that vacuum will when you create a vacuum, then it will compress it will compress the substrate, and the substrate get stick to the rod. Okay, then the next point is the solvent safe bowl and surround. Okay, so basically the inner part is basically that is made up of this Teflon in order to reduce the corrosion. If it is of metal, then we are going to use different types of solvent, okay, acids, okay, that in our solution, and they may get corrode this, make corrosion for this surface. So it is necessary to use take care of that. Next you can see there is a glass lid. Okay, just for our safety purpose, because when we are inserting our substrate, then we are going to add the solution, and when once we add the solution, then we are going to revolve this rotate this substrate with very high speed. Okay, so in just to for the safety purpose, that some of the solution should not come and come out of the system, or the substrate, if it is not properly placed, then it may get out because of the very high centrifugal force. Okay, and in that case it is necessary to have a lead glass. So it is a transparent, so you are able to see what is happening with your sample from outside. Okay, the next one is you can see there is very important is a spirit level, just to ensure that the substrate is evenly horizontal. Okay, so if the system is kept on some table which is not even, then you have to adjust it, and you have to use that bubbler just to ensure that your system is exactly horizontal. Okay, and there are some keys by which you are able to program. You can provide a program. For example, in this case what you can do is you have to provide certain parameters, like you can give the acceleration, okay, with which speed you want the acceleration. So suppose you want to reach 3000 rpm. Rpm means rotation per minute. Okay, so if you want to deposit your sample at 3000 rpm, then from 0 to 3000 rpm, what should be the acceleration, okay, that you can give, what rpm you want to do the coating process, that you can insert. Okay, so right from 2000, 3000 to maximum 8000 you can go, depending upon the quality of your spin coater. So you are able to control, you are able to change this rpm as per the requirement. The next parameter is you can use time. Okay, so once I give some acceleration and it reached to 3000 rpm, then for 3000 rpm how much time I need to spend, okay, so that it will keep that rotation with 3000 rpm for that given amount of time. So generally you can give from few seconds, few tens of seconds to maximum you can give 5 minutes, 10 minutes as per as per your requirement of the material. Okay, so this is what all about the spin coating machine. Okay, now let's try to understand what is how the spin coating machine is able to deposit the thin films. Now here you can see that there are four important parameters or factors which basically affect the spin coating technique. So first is the precursor concentration. Okay, so basically you are going to make a solution. Okay, so you have to be careful that which type of precursor you are using and what is the concentration of that precursor in the solution. Second is the solvent. Okay, which type of solvent you are using. Okay, whether you are using water or you are using some methanol, okay, or the liquids like that. So I have some examples of that different types of solvent that I will show you in my next slide. Third one, as I said, the spin coating speed, and fourth one is the spin coating time. So these are the parameters basically which you can control and you while the deposition of this thin film. Now as you can see that the schematic representation of these different stages of spin coating process, where there is a figure A, B, C and D, and you can see that in figure A the first step is of dispensation. Dispensation means you have a substrate and now you are going to put your solution on the surface of the substrate. So that process is called as a dispensation. In the second case, once we, as I said, we have to give some acceleration to reach the maximum speed. So once you started to rotate, then what you can see is that there is around a particular axis the substrate is started to rotate, and there is a and the solution of the solution of the desired precursor is started to accelerate. Okay, then in the third case where you can see that there is a C. Okay, so because it has obtained a certain acceleration. Okay, so there is an force which is acting outward from the center of the spin coating system, and that force, okay, is basically get inserted on this precursor solution, so that the excess solution is started to come out. Okay, so because it has reached a very high rpm like 3000, and now it is constant, so in that case what happens, an equal force is get acted in all direction of the substrate. Okay, on the so that it get thinner and thinner. What the next thing happen is, if you keep continuing that high speed, okay, then what happens, the evaporation of your solvent is taking place. It depends upon your rate of evaporation of the solvent used. Okay, and once it started to evaporate, then your film started to become dry. So when you start to deposit the film, it is liquid which is present on the substrate. Once you complete the spin coating process, then what you have is a dried film on the surface of the substrate. So the rotation of the substrate at high speed generates the centrifugal force. Okay, so this is the force which is basically acting on the in the outward direction. Okay, so that is a centrifugal force. So it due to very high speed, it generates the centrifugal force, and that force is basically get acted on the precursor solution, and the solution started to flows the liquid which is in the uniform direction. Okay, so the liquid is flowing in the outward direction. Okay, but with uniform forces. So during this time, the solvent then evaporates to leave the desired material on the substrate in an even covering. So these are the stages. You see, once you start the spin coating process, then these are the stages where the liquid is slowly get converted into the thick film. Now, in order to get a very high quality and consistent thin film, there are some parameters which are needed to take care of these parameters. Okay, first is the substrate should have reached its desired rotational speed before the dispense happens. Now there are two ways, okay, of deposition. Okay, so in one case, what some in some laboratories is done is that first they pour the liquid, okay, and then they close the lid, and then they start to rpm. This is one case. In second case, what you can do is once you reached at that rpm, then immediately during that rpm you can insert the solution on the surface of the substrate. So depending upon that, the quality of the thin film will get changed. So the ink, okay, so ink is nothing but the precursor solution. Okay, so in most of the, this is a very common word when you are using this sol gel technique. So ink is nothing but what the precursor solution. So the ink should be deposited as close to the center of the substrate as possible, otherwise you may end up with a gap in the middle. Okay, so where what is the exact place where you have to insert your ink? Okay, so the exact place is the center of the substrate. Okay, first case is your substrate should be in a square form. It should not be I mean square or circular, but it should be allotropic. Okay, from center it should be have an equal distance in all the directions. Okay, just to ensure that we are getting equal forces, centrifugal forces on the liquid. Okay, this is the first case. Second is once so where we have to insert the solution is exactly at the center of the substrate. Okay, if we don't put exactly at the center of the substrate, then what happens is at the end of the deposition, what you can see that at the center of the substrate there is no material got deposited. Okay, as you can see that that image is shown in one of the photograph in this slide. Okay, the next is the ink should be deposited in one quick and smooth action. Okay, so it should, so suppose you want to insert 100 microliter of precursor, 100 microliter of ink, then you have to, in one shot you have to complete that 100 microliter. It should not be like first you just poured 50 microliter and after 2 minutes you poured another 50 microliter, then the quality of the thin film will not be good. Okay, so it is better that you deposit your ink in a one shot but with a smooth action. The ink should be deposited in one and only one drop in order to prevent multiple coats. If you do like as I said, after some time if you again pour some liquid, then what you will get is a multiple layers of your material. It will not be a single thin film. There should not be any bubble blown onto the surface from the pipette. Okay, so when you are taking your ink in the pipette, then you should take care that there is no bubbles which are present in the solution, okay, in the ink. Otherwise these bubbles will get affect on the quality of the thin film. The pipette tip should never touch the rotating substrate. Okay, you have to go close enough, but you cannot touch the tip with the surface of the substrate. Otherwise what happens, there will be some scratch will take place, and that will not give you high quality thin film. Okay, as far as substrate is concerned, okay, so there are some important points that you have to take care. Okay, so common spin coating defect induced film coverage condition. So most of the time when you go into the lab and try to make some good quality thin film with the spin coating, you realize that there are some points where there is not no deposition has happened, or there is an uneven deposition has happened, or sometimes the deposition is not that good, homogeneous, in the sense that it has not covered the full area of the substrate. If it happens, then what are the parameters basically they are affecting this type of, they are making this type of thin films. So the first important point is the effect of dust on the surface. The surface of the substrate should be ultra clean. Okay, there should not be any kind of dust which is present on the surface of the substrate. If there is a presence of the dust, then what you can see is you will not be able to get the deposition around that dust particle. Okay, so the dust, that is nothing but the particulate matter on the particle, affects the spreading of the solution. Okay, due to change in the surface wetting, which results in the streaks in the film. So that you can see on the schematic image which is shown in this in the left hand side of this slide. So where you can see that when the surface of the substrate is clean, then there is some groups are available, hydroxyl groups are available on the surface of the substrate. Okay, but if there is a present of some dust, then you can see the second stage where the dust is there, and the dust uh, has removed these OH groups, and because of that the local surface energy of the substrate has got changed. Okay, and because of that what happens is the quality of the thin film has got changed, and where there was a dust particle and there is no OH molecules. Okay, so the surface energy has got changed, and because of that you can see that there is a particle, there is a region where your ink has not get sprayed homogeneously. Okay, so this is the effect of dust on the quality of the thin film. Okay, second is that is also very important parameter, which is the weighting property of the substrate. Okay, so if you want a very high quality of the thin film, then you have to ensure that the surface of the substrate is hydrophilic. Okay, if the surface of the substrate is hydrophilic, that is nothing but the its a contact angle is less than 90°, then the quality of the thin film is very high. Okay, because the surface is hydrophilic, it is allowing all the solution to spread very nicely, and you get a good quality film. But if it is hydrophobic or super hydrophobic, then what you can see is there is not a good coverage of your material on the surface of the substrate. So that will hamper the homogeneity of the thin film coating on the surface of the substrate. Okay, so non-uniform liquid expansion during spinning due mainly because of the imperfect substrate wetting. So if your substrate is not properly wetting, in some region it is hydrophilic, in some region it is hydrophobic. Okay, then that kind of substrate will give you a non-uniform thin film. Okay, so areas of the substrate remain uncoated, which occurs often if the initial liquid volume is too small. So this is another parameter, that how much amount of liquid you are trying to pour during the spin coating. If so that amount of liquid you have to optimize as per the size, as per the area of the substrate. So if your area of the substrate is very high and you are taking a very less amount of volume of your ink, then what happens? Then the problem is, in that case also you are not getting uniform coverage of the thin film. Okay, so next point is, which are the factors which affect the thickness of the spin coated thin film. Now you can imagine this. This is easy to understand. The first is a spin precursor concentration. Okay, so this is easy to understand, because if the precursor concentration is high, then the thickness of the thin film is high. If the precursor concentration is low, then the thickness of the spin coated thin film will be low. So this is directly proportional to the thickness of the thin film. So if the solubility of the precursor is higher, the concentration of the solute in the solvent becomes high, results in a thin film with high thickness after spin coating, right? Higher concentration affects, high concentration means basically we are making more viscous ink, right? And thus non-linear relationship will be developed. At low concentration, the thickness of the film is approximately linear, dependent upon the concentration of the material in the ink. So it is easy to understand that basically the precursor concentration is going to affect the viscosity of the solution. If it is very high concentration, means it is very highly viscous, then the thickness of the thin film will be high. Okay, and if the precursor concentration is less, then viscosity is less, and what you get, the final product is the thin film. Second is again is easy to understand, is the spin coating speed. Okay, so here what you can see is that the spin coating speed is showing non-linear relationship. Okay, so generally in general the spin coating can produce uniform films relatively easily from about 1000 rpm upwards. So below 1000 rpm, again the quality of the film will not be good, but at 1000 rpm the thickness of the thin film is high. As you are increasing the thickness from 2000, 3000, 4000, its thickness is going down. But once you go above certain rpm like 6000 or 7000 rpm, then what happens, there is no much change in the thickness of the thin film. So most common spin coaters will reach a maximum speed of 6000 to 8000, although specialist coaters may go to 12,000 rpm or higher. But as I said, after certain rpm like 6000 to 8000 rpm, there is no much change in the thickness of the thin film, and that is why most of the companies are just making limited rpm like 8000. In a special case, you can go above 10,000. So that spin coating thickness relation with the rpm is shown in the right hand side graph. Okay, so in general the thickness of the spin coated film is inversely proportional to the spin speed. So as I said, there is a effect of spin coating time. Now this time you have to decide on depending upon which type of solvent you are using. Okay, which type of solvent you are using. So for most standard spin coating techniques, the objective is to keep the substrate spinning until the film gets fully dry. So what is the requirement is when the rpm gets stops, okay, the deposition of thin film with spin coating gets stops, then what should we should get is the dry film. We should not get a film which has a lot of still liquid in that. Okay, so as such, this will mainly depends upon the boiling point and vapor pressure of the solvent. Okay, so which type of parameters are there? So the parameters of solvent which you are using. So what is the boiling point of that solvent, what is the vapor pressure of that solvent, that is very important to know before use. And if you know about that, then accordingly you are able to control, you are able to provide that sufficient amount of time. In addition to that, you can also need to take care about what are the ambient conditions, that is what is the temperature, what is the humidity, okay, while you are performing the spin coating. So if you are doing spin coating at room temperature, then the things are different. But if you are doing the spin coating with a high temperature, then it will not be the same parameter you have to follow as compared to room temperature. Okay, so some of the solvent parameters are shown here. So if you generally take water, IPA, ethanol, methanol, these kind of solvents, then 30 seconds is usually enough for so that after that amount of period the solvent get evaporated. But if you take a dichlorobenzene, trichlorobenzene, okay, and glycerol, this kind of solvents as a precursor solvents, then what you have to do is you have to wait for longer spin time. Okay, so here is 30 seconds, but there you may need 2 minutes, 3 minutes, 4 minutes, 5 minutes, depending upon their boiling point and vapor pressure of the solvent. So for a higher boiling point, and or lower pressure, okay, solvent drying may take considerably longer. Okay, as I said, maximum you have to wait for 10 minutes. So here is an what are the advantages and disadvantages of spin coating technique. Okay, so you can see advantages. This is a simple and relatively easy to set up, and that's why, as I said, that it is in most of the laboratories the spin coating technique is available because it is simple and relatively easy to set up. Second is thin and uniform coating can be achieved. So the quality of the coating is high. You get a thin, as at the same time you get a uniform coating. But as I said, you have to take care of all the parameters which we have discussed in our last slides. Due to the ability to have high spin speed, the high airflow leads to fast drying times, which in turn result in high consistency at both macroscopic and nanolength scales. Okay? So these are the advantages of this spin coating technique. So what are the disadvantages? There are two disadvantages of this technique. First is it is an inherent batch, that is a single substrate process, and therefore has a relatively low output. Okay, so if you have a spin coating machine, then during at a single time you have to deposit on a single substrate. Okay, multi substrate deposition is not possible with spin coating process. Okay, whereas if you remember, in chemical vapor deposition we have seen that there is a batch of 25 substrate where you are able to deposit them at the same time. Okay, but here in spin coating process you have to deposit one substrate at one time. Second is the actual material usage in spin coating process is typically very low. Okay, that is around 10% or less. What does it mean? So what you the precursor you are using, so as I said, you are using some 100 microliter of precursor you are poured. Okay, that ink, okay, you are using the volume with the volume of 100 microliter. Out of that 100 microliter, only 5 to 7 to 8% of the precursor was utilized for the deposition of the thin film, and the rest, more than 90% of the precursor, has gone off as a waste. Okay, has gone off as a waste. So this is a major disadvantages of this technique. Now there is a one more last technique, as I said, which is nothing but the deep coating process. So this is a sol gel coating for deposition of thin film with the help of deep coating process. So this is simple to understand. Again, as I said, okay, so in the deep coating process the substrate is immersed in a sol and then withdraw with a well defined speed under controlled temperature and atmospheric condition. So it is easy, as easy as you are dipping your biscuit in the tea cup of a tea, right? Okay, but here scientifically what you have to do is the rate of dipping and the rate of withdraw you have to control. Okay, so that if you do that kind of thing, then what you can see in the schematic image on the top on the top side is that there is a sol is present, so colloidal particles are suspended in that, and once you are dipping your substrate in the solution, then what happens when you are taking it with a well controlled withdrawn speed, then there is a deposition of these nanoparticles on the both sides of this substrate. Okay, the coating thickness again now depends upon various parameters like viscosity of the coating solution, immersion time, withdrawal speed, evaporation rate, Okay, so all these parameters are basically are going to tune the thickness of the coating. For example, to get the film with low thickness, if we want low thickness, then viscosity of the liquid should be low. Okay, and withdrawal speed should be high. So you are not allowing enough time for these precursor solution, okay, to get it dry. Okay, so so you directly so you are taking that substrate out with a very high speed. So in that case, what you get is a low thickness. Okay, if you do opposite, then you get a high thickness. Next stage is gelation to densification process of the thin film, thin layer done by annealing it to obtain the oxide coating. Now there are two types of coating machines are there. So this is the coating machine I have shown to you. Okay, that is, the company is from Hallmark, which is an Indian company, which is situated in the Bangalore. Okay, so basically they are going to provide you this kind of machines. Okay, so they have basic two types of these machines. One is a deep coating unit, that is a basic model. Okay, and right hand side you can see deep coating unit with heating dryer or with infrared dryer. Okay, so what you can see, if you see this machine carefully, okay, so what you can see that there is a rod. Okay, there is a base which is given just to keep your precursor solution in the beaker, so you can keep your beaker there. Okay, and on the right hand side there is a panel, and where you can give a program. Okay, so you can decide the rate of disperse, okay, dipping, rate of dipping, and then you wait for some time, and then rate of withdraw. Okay, and then you can get a film on the surface of the substrate. On the right hand side you can see that, okay, there is a beaker which is kept, and there is a one kind of a chamber is there. Okay, so that chamber is nothing but the heating chamber. Okay, so in that case, what you can do is, once you withdraw the film, it is still wet in condition, so that wet get dried in the small heating tube furnace. Okay, so that you can see with this. So both this system is available. Again, as I said, this is a very low cost system and easily available in most of the laboratories. So an infrared heater, okay, a normal heater is a body with high temperature which basically transfers energy to body with low temperature through electromagnetic radiation. So infrared heater is slightly different than our conventional heater, and but the purpose is same. Okay, just to dry the coated thin films. Okay, now here in additionally what you can do is, you there is a one more unit which is called as angle dependent deep coating unit. Okay, angle dependent deep coating unit. Now in the last slide what I have shown you is, there is you cannot change the angle of dipping and withdraw. Okay, so if you want if you want to do that at different angle, then there is some special arrangement is done, where you can see that you are able to rotate this entire setup. Okay, so that you can do that entire dipping and withdraw process at that particular angle. So in an angle dependent deep coating process, the coating thickness is dependent on the angle between the substrate and the liquid surface. So this is you can remember to our first type, where we discuss about this wet flow coating. So there is also a relation of angle with the thickness, so that same relation is also follows here. Okay, so different layer thickness can be obtained on the top and bottom side of the substrate. So you can see this in the right hand side schematic image. So because, as I said, in the advantage of the deep coating process is you are getting the coating on both the surface of the substrate. Okay, not only top substrate. Okay, but here what you get is the coating on the both sides of the surfaces. But if it is exactly vertical, Okay, then what happens, the thickness on both the sides will be equal. But if you do this at a particular angle, dipping and withdrawal, then what you can see is the thickness what you are getting on the top and in the back side is of different thickness. The substrate is drawn out of the coating solution under a well-defined angle of inclination. So dipping angle can be ranged from 0 to 45 degree. Okay, if it is 0, then it is a normal dip coating process. If it is above 0 to 45 degree, then it is angle dependent. Both surfaces are coated simultaneously, resulting in different film thickness on front and back side. As I said, one of the advantage of ADDC is the reduced number of layers or coating steps to obtain desired thin film properties. Okay, so this is an advantage that you can reduce the number of layers, okay, or coating steps, because if you have any kind of substrate, okay, cylindrical rod, if you have even that kind of substrate, is possible to coat on from inside and outside with the help of this deep coating process. But it is not possible to do that for the spin coating process. Okay, so this is all about the three types of coating processes, where basically we are using a sort of sole, and then afterwards it get converted into gel, and then we just dry it and get the desired film in the form of a coating. So we'll stop here, and we will see our next technique in the next lecture. Thank you.